All right, this is Physics CP, the first day of the spring semester, making it January 25th, 2021. The new unit of study called Segment 3, the scope is called Energy and its Applications. Ha! And we're supposed to spend 5 weeks on this. So I'm going to start with math and probably end with math and do everything with math because I love math so much, sillies. And the math that we need to review is trigonometry. So I'm drawing myself a fine, beautiful looking right triangle. Haha, yes, there it is. On this right triangle, the longest leg is called the hypotenuse. If I draw this symbol here, that's the Greek letter theta, and theta is drawn to represent the reference angle, the change in direction from one side of this right triangle to the other side, this angle. The side or leg of this right triangle that is closest to this reference angle, that is not the hypotenuse, is the adjacent side of this right triangle. And of course, going to the opposite side of this right triangle is the leg that is referred to as being the opposite leg. If we set this thing up on a Cartesian coordinate system, the adjacent side is along the positive x-axis. The opposite side is parallel to the positive y-axis. And the part that you've memorized and that you love from math class is SOHCAHTOA. A reminder, SOHCAHTOA is talking about the ratios of trigonometric relationships between the three sides of any right triangle. It says the sine function, the sine of any angle, is the ratio of the opposite side divided by the hypotenuse. The cosine of any angle theta is the ratio of the adjacent side divided by the hypotenuse. The tangent of any angle theta is the ratio of the opposite side divided by the adjacent side. Hence, the mnemonic memory device SOHCAHTOA. Or as my math teacher once told me in high school, Oscar had a hairy old aunt as a way to memorize SOHCAHTOA. And just because I love math so much, I kind of feel compelled to point out to you that if I take the sine of theta, which is the opposite over the hypotenuse, and I divide all of that by the cosine of theta, which is the adjacent side divided by the hypotenuse, guess what? The hypotenuses are both in the denominator, so they cancel out. Well, I should say the denominator of each fraction, they cancel out. And so the tangent of theta is the sine of theta divided by the cosine of theta. That is just a true trigonometric identity. Not that you're going to be using it, I just thought I would share it with you. Okay, so among other things, to do this sort of work, I want you to be competent in using the cosine function in particular. So if I have a right triangle and it's a 3, 4, 5 right triangle, and I want you to tell me the value of the angle, that's where you have to start using the inverse trigonometric functions. In this case, theta would be the inverse sine of 3 over 5. And if you put that into your calculator, you'll get an angle out. The cos theta is also the inverse cosine of the adjacent side, 4 in this example, divided by 5, the hypotenuse. We can also say that theta is the inverse tangent of the opposite side, 3, divided by the adjacent side, 4. All three of these will give exactly the same angle. When you use a calculator, I'm going to be using a TI brand graphing calculator, programmable calculator. If you have a Casio, they have slightly different labeling and instruction set, and I'm not very familiar with it, so you're mostly on your own. But if you have any kind of TI, 81, 82, 83, 84, 84 plus, 84 plus color edition, this is as high as I go. If you're using one of those fancier ones, yikes, consult your owner's manual. But there is a button labeled mode. Let's see. I'm going to make it a little darker. Here's the button labeled mode. When you press it, your screen shows you all kinds of capabilities. Of course, this one shows more than a TI-84 3 or 2. Things I want to point out to you that you should know as students. Normal, the one that's flashing right now because that's where the cursor is highlighted, is the way you're used to seeing numbers. Psi is short for meaning always display the numbers in scientific notation. So instead of displaying the number 3, it would display it as 3 times 10 to the 0 power. Let me see if I can give you an example. So I'm going to select that, quit this, and say, what is the number 3? And it will say, oh, that is 3 times 10 to the 0 power. If I had it in normal, it would have just said 3. Okay, so that's what psi means. As a humorous comment here, I ask my students, what do you think ENG stands for? And they say, oh, that means put it in English. But no, it doesn't. It actually means put it into engineering format. In engineering format, that is adjusting the exponent to always be a multiple of 3. That matches the Greek prefixes kilo. Kilo is 10 to the 3. Mega is 10 to the 6. Giga is 10 to the 9th. And so forth. Tera, 10 to the 12th. Milli, 10 to the negative 3. Micro, 10 to the negative 6. So if I put it into engineering form, it will always adjust the exponent to be a multiple of 10 to the 3rd power. So if I ask it, what is the number 3 now? It should just say 3, well, times 10 to the 0 power. Okay, I'm sorry. If I ask it, what is 1,300? It'll say, oh, that is 1.3 times 10 to the 3rd power. And you're thinking, oh, that's scientific notation. But what if I ask it for 13,000? Okay. Well, in normal mode, that would just say 13,000. In scientific notation, that would say 1.3 times 10 to the 4th power. In engineering format, it will say 13 times 10 to the 3rd power, meaning 13 kilo whatevers. So anyways, as long as I'm showing you what the mode button does, I thought I'd explain to you what ENG stands for. Most of the time, I use my calculator in normal mode, same as you. Float means the decimal point goes wherever it seems to fit best for the given problem. is one way of putting it. These numbers to the right mean override that. If you select 0, it will round everything off to integer format. If you select 1, it'll always display the number to the nearest tenth of a value. 2 to the nearest 100th. 3 to the nearest 1000th. So these numbers represent how many values to the right of the decimal point it's going to display the number. So if I put in 8, for example, and I put in that 13,000 again, it's going to display it as far as it can go, 8 digits out total, I suppose. Who knows? Yikes. Anyways, like you, I tend to keep this in float mode. Here's the one part that you really need to check on your calculator. If you're in math class, quite often, you'll have to work in units of radians. But here in physics class, we are going to be working in units of degrees in this course. In college physics, yes, they will be using radian mode. And in aerospace, we worked in radian mode much, much more than in degree mode. There's more to your calculators. The rest of this stuff we don't care about today, so let's not worry about the rest of this for now, right? This is the only thing I really care about that you check on your calculator. Go to the mode button, verify that it's set for degrees, not radians. Okay, so we're good to go. Now, let's take a look at some situation here and say, what if I have a right triangle and this angle is 20 degrees and the hypotenuse is 12 meters, 12.0 meters. And my question for you, so what is the length of the adjacent side for it, the x component of it? You should look at this and say, oh, okay, this is, after all, the adjacent side that I'm asking about, and the hypotenuse is given, and the angle is given. So SOHCAHTOA, I should choose the cosine function to figure out the adjacent side. The cosine of theta is the adjacent side, I'll just write x this time, divided by the hypotenuse. To solve for the lengths of the adjacent side, I would multiply both sides by the hypotenuse. So the adjacent side x is equal to the hypotenuse times the cosine of the angle. And this is always going to be true. This is a generically true statement, no matter what my value of x and theta is. In this example, I would type in 12.0 meters times the cosine of 20 degrees. Okay, I've asked my students what the answer is, and let's work it out on the calculator. So on my calculator, what you would type in is 12 cosine 20. Strictly speaking, a TI is so smart, if you press the enter key, it'll end the expression. But if you want to be, I don't know, pure about it, you can do a close parentheses before you press the enter key. Enter. It displays the value 11.27631145. Of course, you say these are insignificant digits. And let's round it to just 3 sig figs, making this 11.3 meters. So at least one student got that correct. 11.3 meters is the value of x. One comment I want to make about angles. Let's please not apply significant digits to angles. So if I say the angle is 20 degrees, don't say, oh, I'm going to round my answer to 2 sig figs. Instead, don't use the sig figs and the angles as the limiting factor for sig figs. I could go into a long explanation as to why not. Let me try suggesting, look, what is the difference between 359 degrees and 360 degrees? That's, to 3 sig figs, that's a difference of 1 degree, right? What's the difference between 0 degrees and 1 degree? Well, that's like, oh, I only know it to 1 sig fig between 0 and 1. But really, this is a change of 1 degree. This is a change of 1 degree. So it's not correct to think that this is 3 sig figs and this is 1 sig fig. So we're just not going to apply sig fig rules to degree measures. So whether I say it's 20 degrees with a decimal point, or if I say it's 10 degrees without a decimal point, let's just not apply the rules of sig figs to angular measure. You can apply it to the trig functions afterwards. So if I said this is 12.0 meters to 3 sig figs, then yes, after you do your trig calculation, round it to 3 sig figs and go on from there. All right. The math review that I care about is so that you can use the cosine function for the work that we're going to be doing now. Sometimes you might need to do the sine function as well. So maybe we should do a practice problem with the sine function as well. So I have a right triangle, and the angle is 38 degrees, and the hypotenuse is 17.3 meters. Calculate, please, what is the y value for this right triangle? What is the height of this right triangle? All right, so my students have correctly calculated that I'm going to use the sine function for this. The hypotenuse is 17.3 meters. The angle is 38 degrees. To solve for the opposite leg, I multiply both sides by the hypotenuse. I put it into my calculator, and the result that comes out, 10.65094,352, rounded to 3 sig figs, becomes 10.7 meters. Alrighty. What if I didn't give you the hypotenuse? What if I gave you one of the other legs instead? Let's say I told you the angle is 50 degrees, and the opposite side is 21.2 centimeters. And I want to know what is the length of x in this problem. Calculate, please. Solve for x. Great. I see I forgot to hit the record button while I explained all the answer. So let me blitz through it really quickly. To solve for the adjacent side, x, I use the tangent function. I said the tangent of the angle is equal to the opposite side, which is the y value, divided by x, which is the adjacent value. To solve for x, I'm multiplying both sides by x to get it out of the denominator and up into the numerator. On the right, that cancels. On the left, I have x tangent theta is equal to y. I then divided both sides by the tangent of theta. So I had x is equal to y divided by the tangent of theta. When I plug in the actual values, 21.2 centimeters divided by the tangent of 50 degrees, I get a value of 17.8 centimeters for this example problem. And this crude sketch here is where I was starting to tell you, look, going forward, I want your math skills to be kind of on top of things. For any right triangle, if I give you any two sides, I want you to be able to calculate the angle or calculate the third side using Pythagorean theorem. So if I tell you this is 5 and I tell you this is 3, I want you to say, oh yeah, 5 squared minus 3 squared is 4 squared. And say, oh, okay. And if I need the angle, use SOHCAHTOA and tell me what's the value of this angle. Or by complements, what's the value of that angle? Great. So now, maybe time for a new sheet of paper. You're going to be calculating work. Work is a physics term, and it is defined as the dot product of force and displacement. Wow, the dot product of force and displacement. Force and displacement are vectors. That means they have a magnitude and they have a direction. Work is a scalar quantity, and it just represents the magnitude of, in this case, energy, which is work. Work and energy are the same thing. The units of force are newtons. The units of displacement are meters. When I calculate the product of newtons times meters, the units are called joules. So capital J for joules, capital N for newtons, lowercase m for meters. And now what does the dot mean in the dot product? It means I multiply the magnitude of the force by the magnitude of the displacement by the cosine of the angle between these two directions. Okay, so let's look at some examples here. Suppose I have a box and I pull the box to the right with a force of 10 newtons. And the box moves to the right, a displacement of 3 meters. Then the amount of work done to move this box with that force, that constant force, over this displacement would be 10 newtons times 3 meters times the cosine of the angle between F, which is to the right, and the displacement, which is also to the right. These are pointing in exactly the same direction. The angle between them is 0 degrees. If you don't believe me, ask your calculator, what is the cosine of 0 degrees? And it will tell you the answer is 1. The cosine of 0 degrees is 1. And by the way, later on, the cosine of 90 degrees will be 0. The cosine of 180 degrees is negative 1. And for any angle in between, it's going to be between these values, as you go through the different quadrants. Okay. So in this case, you can do it in your head. Cosine of 0 degrees is 1. 1 times 3 times 10 means 30.0 joules of work is done in this example. 30.0 joules of work is done when a 10 Newton force acts over a displacement of 3 meters. Let's do another example. What if I apply a force of 18 newtons and the box goes 9 meters to the right and then it goes 2 meters back to the left? How much work is done? Well, the answer is 18 newtons times the displacement. Now, the displacement means take your final position wherever you end up and subtract from that your initial position wherever you started from. That is your displacement. So even though you went 9 meters to the right and then you went 2 meters back to the left, your displacement is going to be just 7 meters in this example. And the force was to the right, and the displacement was also to the right. The angle between to the right and to the right is 0 degrees. The cosine of 0 degrees is 1. So on your calculator, you're going to go 18 times 7 to get 126 joules of work done to 3 sig figs in that example. Let's do another example. I have a box and I lift this box. Now this box weighs 25.0 newtons. And I lift the box up 2 meters. How much work do I do lifting this box? Okay. And by the way, I lift the box with a force equal to its weight. So its weight actually points down, and my applied force points up. So I should specify, what work am I talking about? The applied work, the upward pointing work, is going to be 25 newtons times 2 meters times the cosine of the angle between up and up. The angle between up and up is 0 degrees. It's not 90 degrees because they're both pointing the same direction. That's what we care about. If they're pointing the same direction, then the angle is 0 degrees between them. And so this one you can do in your head. 25 newtons times 2 meters times the cosine of 0 degrees is 50 joules of work is done. As a separate physics question, how much work is done by gravity in this same problem? Well, the weight of this object was 25 newtons. And that's pointing downwards. So its magnitude is 25 newtons. The magnitude of its displacement is, again, 2 meters. It went up by 2 meters. But here is the difference between up and down. The force of gravity is down. The direction that the box was moved was up. And the angle between up and down is 180 degrees. As I showed you earlier on the calculator, the cosine of 180 degrees is -1. So 25 times 2 times -1 means the work done by gravity is negative 50 joules of work. And yes, it's possible to do negative work in a physics problem. I know this looks like an equal sign. It's just a huge minus sign there in front of things. Okay, so here's a question. Suppose I have a wood block. Now, this wood block actually weighs 50 newtons. But I'm going to lower it down through a distance. I'm going to drop it, value of minus, let's say, 2.1 meters down. And I'm actually going to lower it using a force that is less than what it weighs. Now, if it weighs 50 newtons, force of gravity, and I lower it using just a force upward, a tension, I guess you would call it, of, how about 18 newtons? Okay, I can ask you, well, what's going to happen? Yikes, this is a crazy situation, but it can happen. In fact, something like this might show up on your homework. So I have this 50 Newton block, that's how much it weighs. I'm going to use only a tension of 18 newtons, which is going to be pointing upwards, by the way, to lower this block by 2.1 meters. Okay, so if I did a free body diagram, the force of gravity pointing down is going to be much longer than the tension force pointing up. But still, we can do some calculations. How much work does the tension do on this block? So the work done by tension is going to be the magnitude of the tension force, 18 newtons, times the magnitude of the displacement, 2.1 meters, times the cosine of the angle between the upward tension and the downward direction that it actually moves. Oh, I shouldn't put this here. It moves downward. So this means it moves downward. Okay, so that angle between up and down is 180 degrees. So here I have to go 18 times 2.1 times negative 1, and I do negative 37.8 joules of work lowering this block. Okay, crazy as that sounds, I do negative 37.8 joules of work. But wait, there's more. Gravity also does work on this box at the same time. And the work done by gravity is going to be equal to the force of gravity, which in this case is the weight, right? 50 newtons is the force of gravity, times the displacement that it moves down vertically, 2.1 meters, times the cosine of the angle between the direction of the force of gravity, which is down, and the direction that it moves, which is also down. Well, the angle between down and down is 0 degrees. And the cosine of 0 degrees is 1. So if I calculate 50 times 2.1 times the cosine of 0 degrees, I get 105 joules of work done on this object by the force of gravity. But wait, there's more. if I add together all the work that was done on this block, we call that the net work that is done on the block. So if I take positive 105 and add to that negative 37.8, the net work is 67. And unfortunately, I can't really carry it out to 4 figs. So to the nearest whole joule, it's 67 joules now. That is the net work done on this block. Guess where that work ends up? That's a rhetorical question. I'm not really expecting you students to tell me the answer. I will tell you. This becomes kinetic energy. Yep. So physically what's going on is you're letting this block fall down, and the forces don't cancel, so it's not a constant speed, it's accelerating. It's falling down faster and faster. This much energy is being added to this block. So if it started from rest and you add this much energy to it, then it becomes possible to calculate what is its speed after this much energy has been added to it. Well, the formula for kinetic energy is 1/2 times the mass of the object times its velocity squared. I don't have the mass of the object. I have the weight of the object. But I know from physics class that weight is the product of mass times acceleration due to gravity. So if I rearrange that equation and take the weight divided by 9.8, then I'll have the mass of this object. 50 divided by 9.8, enter, beep, 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 and it says 5.10. Those must be kilograms. I've just calculated that the mass of this object is 5.10 kilograms. It gained 67, there's no decimal point here, 67, I know it looks like a decimal and I can't erase it, 67 joules of kinetic energy. If I want to figure out how fast is it moving now, I solve for its speed by multiplying both sides by 2, dividing both sides by the mass, then taking the square root. So V would be equal to the square root of 2 times the kinetic energy divided by the mass, all underneath the radical sign. So that's going to be 2 times 67 joules divided by 5.10 kilograms, then take the square root of that. Okay, so in agreement with some of my students, I get a value of 5.13 meters per second. That's the speed that this block is moving at the end of this problem. If I had more class time, and I'm down to 1 minute, I sort of feel, gee, I would have loved to have solved this problem using Newton's laws of motion and the net force from the free body diagram and calculate the acceleration and use the kinematic equations of motion. I can't do that carefully in 1 minute. I can certainly do it at ludicrous speed in 1 minute and say, well, okay, look, 50 newtons, minus 18 newtons is 32 newtons. If I divide that by the mass, 5.10 kilograms, then the acceleration is 6.27 meters per second squared. And if I use the fourth kinetic equation of motion and take the square root of 2 times that acceleration times the distance through which it fell, then sure enough, like my calculator says in the end here, I get exactly the same answer within rounding off 5.13 meters per second. My point being, you could solve this the old-fashioned way, but we're going to practice using energy and work calculations to do this type of work.